Binding energy. The mass of an atom should be the sum of its constituent particles, that is, electrons, protons, neutrons. But the mass of any permanently stable of atom is found to be less than the sum of the masses of its contents. The decrease in mass is known as mass defect. It has been suggested that the mass is converted into energy which formed in the formation of given nucleus for individual protons and neutrons. The release of energy results in the stabilization of nucleus. That is, protons helps in binding the nucleus, and hence it is called binding energy. That binding energy of a nucleus may be defined as the amount of energy released during the formation of nucleus from its protons and neutrons. Mass defect. Delta M is equals to ZMH plus A minus ZMN minus Z power M power A. This is equation 1. Z is equals to atomic number of isotope. Mh is equals to mass of the hydrogen atom. Mn is equals to mass of the neutron. A minus Z is equals to number of neutrons. A is equals to mass of the isotopes. Z power M power A is equals to isotopic atomic mass. Hence, binding energy Be. Eb is equals to delta M into C square. Eb is equals to ZMH plus A minus ZMN minus Z power M power A into C square. This is equation 2. The binding energy may be either expressed as of AMU or MEV. AMU is equals to 931.478 MeV. Aston in 1927 expressed the deviations of the masses from mass numbers in the form of a packing fraction for each nuclide given by packing fraction F is equals to Z power M power A minus A by A. F is equals to Z power M power A by A minus 1. 1 plus F is equals to Z power M power A by A. Z power M power A minus A called mass excess. The binding energy per nucleon in terms of mass unit. B bar is equals to B by A. B bar is equals to Z by A mH plus 1 minus Z by A mn minus Z power M power A by A. B bar is equals to Z by A mH minus mn plus mn minus 1 plus F. B bar is equals to Z by A into 1.007825 minus 1.008665 plus 1.008665 minus 1 minus F. B bar is equals to minus Z by A into 0.00084 plus 0.008665 minus F. Variation of binding energy with mass number. With the expectation of He4, Be8, C12 and O16, the values fall on in approximately to a single curve. The binding energy of some of the lighter nuclides such as H1, He2 and He3 are very low but over very considerable range of mass numbers. The Be per nucleon is close to 8 MeV. The positive value of B by A for all values of A shows the stability of the nucleus. This shows that there will be attractive nuclear forces between these constitute within the nuclear volume. There is a rapid increase in the value of B by A for light nuclei with A not able peaks at A is equal to 4n He4 Be8 C12 O16 Mg24. The nuclear forces are saturated discontinuous in the plot for observed by several workers at 7 or n equal to magic number in the curve V by A vs A. Semi-empirical mass formula. In 1935, von Weizsäcker expressed the atomic mass nuclide in terms of the series of binding energy correction terms with the main mass contribution from proton and neutron. The modified expression of the mass is known as semi-empirical mass formula. The mass of the neutron atom can be expressed as z power m power a is equals to zmp plus zmc plus a minus zmn minus delta m is equals to zmp plus me plus a minus zmn minus eb. Zm power a is equals to ZMH plus A minus ZMN minus EV. This is equation A. Value of EV is calculated empirically as made up of number of correction terms given by EV is equals to EV plus ES plus EC plus ER plus EP plus EM. This is equation B. Volume binding energy. There will be attractive nuclear forces between nucleons within the nuclear volume. Since the volume of the nucleus is proportional to A, hence this term may regarded as volume binding energy, exchange energy. We may assume that the total binding energy of nucleus is proportional to the number of nucleons A in it. That is, EV is proportional to directly proportional to A. This gives rise to EV is equals to AV. A. This is equation 1. E is proportionality constant. AV is proportionality constant. Surface binding energy. Yes, nucleus of atom has some nucleons on its surface. The nucleons at surface of nucleus are less tightly bound in compared to nucleons in the interior. This gives rise to a surface energy is analogous to the surface tension of a liquid. It is proportional to R square or A by A power 2 by 3 or S is equals to minus AS A power 2 by 3. This is equation 2. ES proportional to 4 pi r square. Es is equals to minus ASN 4 pi r naught a power 1 by 3 whole square gives rise to Es is equals to minus AS power n 4 a r naught square into a power 2 by 3. Es is equals to minus AS a power 2 by 3. Coulomb energy EC. The only long-range force in the nuclei is the Coulomb repulsion between protons. Due to this repulsive forces, the binding energy decreased, assuming that the nuclear charge Ze is uniformly distributed throughout the nuclear volume. The electrostatic potential energy is given by 3 by 5 1 by 4 pi epsilon naught z square e square by r f is equal to fe. Ec is equals to minus ac power 1 3 by 5 1 by 4 pi epsilon naught to z square e square by r is equals to minus ac 1 3 by 5 1 by 4 pi epsilon naught into z square e square by r naught into a power 1 by 3. EC is equals to minus AC into Z square by A power 1 by 3. EC is equals to minus AC into Z minus 1 by A power 1 by 3. This is equation 3. Symmetry energy ER. It has been observed that nuclei are most capable when nucleon contains equal number of protons and neutrons. This condition of stability Z is equal to N is called symmetric. There is a sharp tendency neutrons and protons pair up. As the value of A is increases, the number of neutrons increases rapidly than protons. The excess of neutrons over protons is ER proportional to N minus Z square by A. ER proportional to A minus Z whole square by A. That is ER proportional to A minus 2Z square by A. ER is equal to minus AR, A minus 2Z square by A. This is equation 4. Pairing energy. It has been observed that nuclei contain either even number of protons and even number of neutrons, or odd number of protons and odd number of neutrons are more stable. On the other hand, odd number of protons and even number of neutrons are vice versa are intermediately stable. The pairing effect of charges on binding energy as below. Number of protons Z, number of neutrons A minus Z. Pairing energy. Number of protons even, number of neutrons even. Pairing energy plus delta A power minus 3 by 4. Number of protons odd, number of neutrons even. Pairing energy 0. Number of protons even, number of neutrons odd. Pairing energy 0. Number of protons odd, number of neutrons odd. Pairing energy minus delta A minus power minus 3 by 4. Delta is constant. Magicity energy EM. When a shell is filled by having either the number of neutrons or number of protons equal to the one of the magic numbers, that is 2, 4, 8, 20, 28, 50, 82, 126. A small local maximum in EB as function of A occurs, that is EM is proportional to A. EM is equal to AM into A. This is equation 6. Substitute 1, 2, 3, 4, 5 and 6 in B. EB is equals to AV into A minus AS into A power 2 by 3 minus AC into Z minus 1 by A power 1 by 3 minus AR into A minus 2Z square by A plus or minus delta A power minus 3 by 4. Substitute above equation in A. Z power M power A is equal to ZMH plus A minus ZMN minus AV into A plus AS into A power 2 by 3 plus AC into Z minus 1 by A power 1 by 3 plus AR into A minus 2Z square by A plus or minus delta into A power minus 3 by 4. Applications. Determination of Coulomb radius. Determination of radius for mirror nuclei. To explain the alpha decay. To study the behaviors of isobars in beta decay. To analyze the fission process.